All right, inductance in AC circuits. We're going to discuss the properties of inductance in AC circuits, inductive reactance, and inductive reactance. We're going to compute inductive reactance and inductance. We're going to discuss the relationship of voltage and current in a purely inductive circuit. Once again, there's no such thing as a purely inductive circuit. Inductance happens in a coil. Let's go look at the next thing. Properties we just looked at that, didn't we? Oh, that's didn't switch. All right, be able to compute values for inductors connected in series or parallel, and discuss VARs, which is reactive power. Reactive power is the result of inductive reactance. What a shock, right? Okay. Forgot what I was starting to talk about this. Okay, let's just say, well, you know that a magnetic field is built up anytime current flows through a conductor, right? And in first semester, you learned Fleming's left-hand rule, right? Left, right. What does Fleming's left-hand rule talk about? What is the thumb? Polarity of the magnetic field. Or maybe it's the finger. I don't remember. But we'll discuss that when we get there. Okay, so generally speaking, inductance only happens when AC goes through a coil. Okay? Now, is there a magnetic field built up if DC goes through that coil? Somebody say yes. Okay, it does. But that doesn't create inductance. You cannot transform DC. I'm going to tell you something now that you should write down and remember. And that is, on the final exam, there is a trick question or two. Actually, I stole them from Mr. Lester, and I used them even though they're trick questions. But one of them shows a drawing of a primary winding of a transformer and a secondary winding, and it shows a battery connected to the primary winding. And then it says, what is the voltage in the secondary coil? Well, for a split second, that voltage will spike up when you connect it to the battery. But once it's solid state steady DC, what is the secondary voltage going to read? 0. Because DC does not transform. You can't create much inductance with DC. Okay, inductance in an AC circuit happens when a coil is in the circuit. And it's the result of creating and collapsing a magnetic field. Now, when you're creating, building up, and collapsing a magnetic field, are you doing any work? Somebody say no. So it's sort of like jumping up and down on a pogo stick. You're going up and down, you're doing a lot of work, you're expending energy, but you're not going anywhere, right? Ah, same idea. Inductance is kind of a waste of energy. Inductance AC circuit. Now, we've talked about a couple times where the current that induces the current is opposite in polarity to the induced current. And if they're in the same line, there's what's called counter voltage or counter EMF, counter electromagnetic force. EMF is voltage, right? That's because and that's the reason we use E as a symbol for voltage, right? E is electromotive force, right? And we measure that in voltage. Okay, what's going on here? Inductor reactance is the current limiting property of an inductor. Current limiting. Okay, it creates something like resistance. It's not the same at all. It's counter voltage. The inductor reactance symbol is X sub L. The reactance, the measurement in ohms, just like resistance, Ohm's law formulas can be used. Is that slide really not there? Oh, it is there. Okay. Now, this is a formula you need to remember forever and ever. Write this down if you haven't already. You've actually used it already, I assume, since you did the homework. And the inductive reactance, the X sub L, is 2 pi FL. Now, I want to give you a shortcut. You know, I'm big into shortcuts and mnemonics and things like that, right? Because pi is a number, right? So we have two numbers, 2 pi. 2 times 3.14, right? F, what is F? Frequency. Here in the United States, the frequency is almost always 60, right? And then L is the inductance in henries. It's a number, right? So X sub L is 2 pi F. So if we say 2 pi times 60, we wind up with 2. Well, let's try it before I say it. Pull out your calculator and write, pull up pi, that's in your calculator. Pi times 2 times 60 is what? Say again? 377. Now that's the shortcut we're going to use. Now you're going to have to remember that 2 pi FL is the actual formula. But if you plug in 60 cycles, because that's where we happen to be in the United States, then that number is going to be 377. It gets very simple to use if we say X sub L is equal to 377 times L, right? So if we have an inductor that has a 12 ohm X sub L, because X sub L is in ohms, remember? Okay, so if we have a 12 ohm inductor, how many henries is it? We'd take 12 divided by 377 is equal to L, right? So X sub L divided by 2 pi F is equal to L, right? Everybody agree with that? So X sub L, 12, divided by 377 is what? Point something. 0.0 what? 318? Say that one more time. 0.0318. Okay. 0.031 is 31 millihenries. Remember, engineering notation. In the quizzes in the future, if your answer is not in proper engineering notation, it's wrong. Okay, so writing 0.0318 would be a wrong answer. You need to convert that to proper engineering notation, which is 31.8 millihenries. Okay? Everybody remember engineering notation from the first semester, I hope. If not, we're going to go over it. Don't worry about it. It's just going to be the hard way. Okay, let's go to the next slide. Oh, that's the one I'm on. That's right. I wonder why the previews are not showing up. Okay, now you can see that these windings are round around a single core, right? And you can also see that they're a little farther apart. Coils with turns close together produce more inductance than coils with turns far apart. Shocking, I tell you. Okay. 3 factors determine the induced voltage. The number of turns of wire, just like a transformer. Turns ratio, remember all that? Okay, so the number of turns is always important. The strength of magnetic field and the speed of the cutting action. What determines the speed of the cutting action? That would be the frequency. That's exactly correct. So the frequency is one of the most important things in inductance. And once again, you will work with different frequencies once in a while. If you go to the Air Force and work on a project where they're taking stuff up into an aircraft, that's 400 hertz. If you go to Europe, you're going to work with 50 hertz. Okay, inductance in AC circuits. This is an alternator. Remember that? Okay, it's creating AC. It's going through here. It's got 0.8 henries. Is that in proper engineering notation? 0.8 henries. No. What should that be? 800 millihenries. 800 millihenries. Okay. So the formula is 2 pi FL if we want to find the X sub L. And we would multiply 377 times 0.800, and we get 301.6 ohms of inductive reactance. And that's different from and completely separate from, does this coil right here between this point and this point, does it have resistance? Real DC resistance? Okay, that's separate and different. Totally separate and different. They're different ideas, and they both happen. Okay. Hello? Clearing. Thank you. Why is it not going to the next slide? Wow. I think it jumped several. Okay. Come on. Get it to work yet. No one wants to argue. Okay. Inductance AC circuits. Now you can, in series, inductors can be added up. Does that mean that the inductive reactance can be added up in series? Absolutely. So inductors, you will treat them just like a series resistor. A series inductor, in other words, inductors you treat the same way you would a resistor. So in parallel, what do you think you do? Add them up by the reciprocal method, right? That would be correct. Okay, we're going to come to that in a second, I'm sure. Okay. And here we have parallel ones, and 1 over L1 plus 1 over L2, etc. is equal to 1 over LT, reciprocal formula, because we treat them just like resistors. Now, what you need to know is that the current and the applied voltage happen out of phase, up to 90 degrees out of phase, but it will never be, almost never be, 90 degrees. It'll be some portion of 90 degrees. It will usually not be 90 degrees because the phase angle, oh, we need to talk about phase angle later, but we'll talk about that another day. Okay, and then you can add up VARs because VARs is power. Power is always additive. So when you get into a complex problem where you can't figure it out, go to power. Power is always additive, remember? Except apparent power. But true power, and probably VARs, are always additive. Okay. We already went over all that. We've gone over all of that, and you've read it in your homework anyway. And when inductors are connected in series, total inductance is equal to the sum of the inductors. When inductors are connected in parallel, you add them by the reciprocal method. Sounds familiar. And the total current lags the applied voltage by 90 degrees in a pure inductive circuit, but there's no such thing as a purely inductive circuit either. Okay? And that is the end of that one. So we're going to call this STE17, and you'll see it on the website.